So we have been discussing about this bio-inspired based micro robots. So in this bio-inspired based micro robots, we have been discussing about the different propulsion mechanism which are involved, about the fundamental behind these propulsion mechanism, and then we have also been discussing about the different like characteristics involved in this propulsion mechanism, what are the parameters involved with reference to this propulsion mechanism. So we were more focusing towards this bio based, in fact more on this microorganism based structures and how these structures are deployed with reference to how the propulsion mechanisms are extracted, how it has been transformed into a kind of a mechanical micro robotic system, or in the micro robotic domain for an appropriate application, which we have discussed in detail. Now, as a part of it, we will discuss about these cilia based structure. So, as far as the cilia based structure, the core structure of the cilium was identified as axonomy. So, the single cilium can beat rhythmically and its motion can be divided into two stages. So, one we call it as a effective stroke stage, and the other one we call it as a recovery stroke stage. So when we try to look into the cilium motion of it, so we have one is a kind of an effective and a recovery stroke of cilium, where it has a kind of, so we have seen a kind of a whip kind of arrangement. So this whip kind of arrangement will have 3-4 different nodes. So one, it starts from this effective stroke, it reaches this 0.3 and then it comes back to the one stroke. So it is something like we have, through an effective stroke, it tries to push the whip in the forward direction, and then with the recovery stroke we have a kind of a pulling node. So with reference to a pulling node, you have a kind of a backward notion which tries to just gets generated out of it. Okay, so during the effective stroke, the cilium is straight and pushes a large amount of fluid, and in the recovery stroke it pulls a small amount of fluid as it closes to the cell surface. So in the case of a recovery stroke perspective point of view, so it has a direct relevance towards the fluid. So when it tries to push a large fluid, so of course it gives a kind of a propulsion in the forward, and then when it tries to give a small amount, so it will be a kind of a precise movement which is closer to the system. When the cilia arrange in an array, the hydrodynamic interaction makes the adjacent cilia to beat out of phase. This motion is like a wave-like motion, and it is called as metachronal wave, which is shown over here. So this is a kind of a metachronal wave which is getting generated, and then there is a kind of a cilium kind of structure which is there. So these cilium when due to the alternative effective stroke and the recovery stroke, these metachronal wave can move in an appropriate direction which can govern an appropriate movement. So like flagella, several microorganisms use cilia to generate a drag based propulsion within a fluid. Some of the microorganisms, which includes the paramecium and the stentor, are such microorganisms that uses cilium for a propulsion. So this image will give you a kind of a clarity which talks about the kind of an effective stroke and the recovery stroke in such kind of micro robots. Now, when we try to look into the actuation force perspective point of view, so the cilia beating cycle generates a net translation force due to the difference in the magnetic actuation force between the power stroke and the recovery stroke. So the magnetic stroke torque Tm of cilia with an external magnetic field is determined by Tm, where M is the magnetic moment of cilia and B is the magnetic field intensity. So when we try to look into the magnetic torque, this magnetic torque has a maximum value when the field is applied orthogonally to the magnetic moment. So the equation of the magnetic force on a cilium along with the longitudinal axis of the cilium body can be simplified using a backward power and a forward recovery stroke to the following equation. So we have the Fm equals mb sine gamma by minus theta L. So this corresponds to the applied field angle, theta corresponds to the angle cilium angle, and L corresponds to the cilium length. Also, the cilium angle is evaluated by a simple cantilever deflection model. So this simple cantilever deflection model can be represented as theta equals TL by EI, which is nothing but MB sine minus theta L by EI. So T is the magnetic torque of a planar component of a ciliar micro robot. E is considered to be the Young's modulus of the cilium. I is considered to be the moment of inertia of the structure. Now, when we try to look into the application of these micro robotic perspective point of view, so like when we try to talk about the surface locomotion, these cilia inspired micro robots crawl over the surface, and it is a kind of a mimicking epithelial, it has a mimicking epithelial cell movement. It is highly used for navigation inside ducts, blood vessels, and or on tissues. With reference to microfluidic control perspective point of view, the cilia array can control fluid flow in a lab-on-chip devices. It enables mixing, transport, and sorting of liquid or particles. As far as advantages perspective point of view, the main key advantages of cilia inspired micro robot are, it is designed to work with a low Reynolds number regime, like which is basically inside the human body, and cilia allows a micro robot to crawl or glide along the surface, wall, and tissues. It also enables a local fluid control without external pump, and it is mainly meant for ideal for untethered operations inside the body. As far as flexible and conformal perspective point of view, it is mainly meant for making them safe for in the kind of a WinVo use. So these are some of the advantages of this cilia inspired micro robot. Now let me just discuss about a case study where we have used a kind of a jellyfish inspired jet propulsion system. So as far as in this jellyfish inspired jet propulsion system mechanism is concerned, so this jellyfish inspired jet propulsion model is based on the interaction between the deformable bell structure and the surrounding fluid. So ideally in the case of a jellyfish, we have a structure something like this. You can see it over here. This is a kind of a bell kind of structure, and then there are kind of flagella structures which are available. By giving an appropriate frequency to these flagella kind of structures, the dome moves and these dome moments being appropriately catered. So if you closely observe this dome movement, or if you want to mimic such kind of dome movement based structures, so these propulsion mechanism comprises of two phases. One is called as a contraction phase, where it is called as a power stroke based system. So the jellyfish contracts its bell, it expels the water, and it generates the thrust. So these expelled water forms a kind of a vortex ring that contributes towards the forward motion. When we try to look into the expansion phase perspective point of view, this is a kind of a recovery stroke. So as far as in this recovery stroke is concerned, a bell passively expands, drawing a water into the subumbellar cavity, and the vortex dynamics ensures a continuous moment transfer, enhancing a kind of a good propulsion efficiency. So these are considered to be the two like phases which are being effectively caters towards the propulsion mechanism. Okay, so let me just show you a simple example where shape memory alloy based structures can be integrated to create a kind of a propulsion mechanism. In fact, this case study we had discussed earlier also. As far as in this structure is concerned, so we have a kind of a shape memory alloy which is integrated. So we have two different components. One is a kind of a polyimide structure, another is a kind of a shape memory alloy structure. So these Kapton polyimide sheet or shape memory alloy structures are integrated in such a way that these shape memory alloy structures are carved in a particular, like stitched in these particular polyimide structures, and these shape memory alloy structures are are programmed to get the required displacement. So in order to cater this displacement, so ideally we have a kind of a structure which is flexible, and then we have a kind of an integrated shape memory alloy structure. The actuation motion is scattered by the kind of a elastic structure which is available over here. So what happens is, you have a kind of a medium which takes care of the entire buoyancy or the entire movement of the system. Inside this medium, we have a kind of an actuator. These actuators are ideally kind of a shape memory alloy actuators. So as we all know, these shape memory alloy actuators are programmed to create a kind of a linear actuation, and then during this linear actuation, so there is a expansion and contraction which exhibits, so which like a kind of a contraction phase recovery or a expansion phase recovery which exhibits over here, which scatters the overall movement of the structure. And then in order to cater the frequency, so one way actuation is taken care by the shape memory alloy, and the return stroke is taken care by the rubber string. So ideally your structure looks something like this. This is kind of a Kapton polyamide. This is an SMA structure. So this SMA structure has a capability to actuate in a straight phase. Now what we are trying to do is, we are trying to integrate a string. So this is a kind of a rubber string. So this actuation is taken care by the potential difference once we apply. So once we apply a potential difference, what happens is it becomes straight, and the return stroke is taken care by the kind of a rubber band which is being exhibited over here, which takes care of the overall motion of the system. So that's how this system works. So if we try to look into the overall kinematics which are involved, so where these kinematics are modeled appropriately with reference to a plane and with reference to an axis. So if we see in this particular system, so we have the Q1, Q2, Q3, which takes care of the angular movement theta, and A0, A1, A2, A3 takes care of the overall length between the link and the appropriate movement in the structure. So this is a kind of a model simulation which is being incorporated. So as far as in this model simulation is concerned, if you see, this is a kind of a structure, and the overall structure gets actuated in a particular movement. The forward stroke and the return stroke are catered by the SMA plus the rubber string kind of structure. So through SMA we get a kind of a forward actuation, and the return stroke is taken care by the rubber string kind of structure. So as I had mentioned earlier, so when we try to model this structure, let us consider this as an axis where A and B, so the it basically talks about the, or B talks about the length in the tension, and A talks about the overall elongation in the structure. K corresponds to the stiffness of the rubber spring, B corresponds to the length of the tension, NL the natural length of the rubber string under no load condition, E is the elastic modulus, I is the moment of inertia. So the schematic of the model basically talks about the extract that bending moment which is shown in the actual image, which we call it as a tentacle. So when we try to equate it, so we try to equate it with reference to these equation as well as with reference to the overall displacement which is being exhibited along the axis, along the x-axis. Now when we try to model this structure, as far as the shape memory alloys are concerned, we are well aware about it. So when we try to actuate it, so we try to apply a kind of an electrical pulse to it. So this electrical pulse will cater the actuation, basically kind of like heating and a cooling cycle. So this heating will give an appropriate displacement, and the cooling will take care of the reverse stroke. So which is shown over here. So when we try to plot a graph with reference to the time and with reference to the temperature, so there is going to be a heating cycle, and then there is going to be a quenching cycle. So this alternate heating and a quenching cycle will try to cater the overall biomimicking actuation in the SMA integrated tentacles, so that you have a kind of a stroke moment which exhibits over here, which caters the overall displacement what we are looking for. So when we try to look into the overall variations, or what are the parameters which like affects these particular tentacle movement are, it is based on the modulus variation during the phase change. So we all are aware about the type of SMA phase change. So basically it is a switching between the austenite and the martensite kind of structure. So switching between this austenite and the martensite kind of structure will highly cater the overall actuation behavior. This deflection with reference to change in modulus can be modeled, and the overall deflection is restricted to close to around 30-degree angle, which basically caters the requirement of the actuation. Now, like this is a kind of a simulation which basically talks about where exactly the actuation happens. So if we have a jelly kind of structure, the loading happens along the sides of the tentacles. When the loading happens in these tentacles, and when the forward and the return stroke happens, so what happens is there is a kind of a lift and a drag which will participate in this system, and when there is a lift and a drag participate appropriately, you can see a kind of a movement which persists over here. So the pressure contour during bell contraction and a pressure contour during bell expansion, and then there is a kind of a vortex formation which is visualized via the streamlines. So this is a kind of a real jellyfish simulation. So where we could see this jellyfish swims by contracting its bell and the umbrella shaped part at the top of its body, which forms a kind of a vortex behind the animal, and it propels forward. Either if we consider this like appropriately, if we try to manipulate this vortex motion, we get a kind of a displacement either in the kind of a vertical direction or in the horizontal direction. So your movement, overall propulsion with respect to vertical or horizontal is decided by the module of the contraction and the expansion. So that is why if you see over here, so these are considered to be the key points where exactly we try to focus the load, and this will cater the overall drag force and the lift force. So this alternative drag force and the lift force will be helpful to create a vortex behind, and it will be helpful for a propulsive motion within the system. So this is a kind of a structure. So as far as in this structure is concerned, so it gives us a clarity with reference to the amount of thrust force which is exerted with reference to time t. So there are some restrictions are there when we try to use such kind of soft actuators, basically such kind of shape memory alloy based soft actuators, because when we use such kind of soft actuators, what happens is there is a chance that the overall thrust which is integrated can be brought. However, with reference to frequency perspective point of view, it has its own limitations. So in order to cater that frequency aspect, so there is we may need to compromise on the thrust what we are trying to generate out of it. In fact, this is a kind of a performance evaluation. So in this structure, if you see, this is a kind of a polyamide structure. So it's a tethered kind of system. So where we have a system at rest, and during actuation, it moves in this direction. So here, so in this particular case, so we have a SMA wire diameter. As we are pretty clear with reference to actuation perspective point of view. So we are trying to switch between the Martensite phase and the austenite phase. So when we try to switch between the Martensite phase and an austenite phase, so what happens is we may need to give a pulsed signal to this system. So these pulse signal will be helpful for us to create a kind of an actuation, and it also caters the overall movement what we are looking for. So even though especially in an underwater condition, the overall convection is protected appropriately because of the polyamide film which is being kept over here. However, with reference to actuation perspective point of view, the frequency is constrained within the switching behavior of this austenite phase and a Martensite phase, which is evidently shown over here. In fact, this is a kind of a thermal image camera. So this thermal image camera will give us a clarity like how much is the illumination which happens, or how much is the temperature variation which is being exerted over here. In fact, this is a kind of a performance evaluation. So as I mentioned earlier, the frequency, the switching behavior between the austenite and Martensite will cater the required frequency. So for instance, when we try to look into the frequency of the tentacle, so we have three different types of frequency. One is with reference to 0.5 hertz, another one is with reference to 1 hertz, and then with reference to 2 hertz. So with reference to 0.5 hertz perspective point of view, so we have a very limited structure. So within the structure we can see the overall frequency which exhibits. With reference to 1 hertz perspective point of view, appropriately you are trying to tune the actuation behavior to get the structure, and with reference to 2 hertz perspective point of view, so we can have an appropriate structure what we are looking for. So these performance evaluations, these actuation behavior has a direct relevance towards the functionality and the characteristics of the system. Now this is the kind of the actual structure. So in this actual structure, we have a kind of a camera and an electronic control system which is being placed on top of the dome. Then there are certain amount of flex sensors are there, and this is the kind of a tentacle which is integrated with SMA structure. So the actuation with this SMA structures are deployed, and the overall actuation behavior is studied using a kind of a flex sensor. So this flex sensor acts as a kind of a medium to study the deflection behavior as well as the characteristics. And then you have an onboard camera and an electronic control system which is placed on top of it, so which is mainly meant for measurement related applications. So the overall bending angle and the time is measured using this tentacle, using this system. So where we have a kind of a tentacle bending angle. So in this tentacle bending angle, we can see a kind of a deflection characteristics which exhibits. So with reference to this deflection characteristics, we can study the behavior. So it's a kind of a system which has a sensor in place and an actuator in place. The actuator is a kind of a shape memory alloy integrated polyimide structure. Sensor is a kind of a flex sensor. Other functional sensors are characterized using the camera and the electronic control system, which is being placed on the kind of a dome kind of structure. So this can be used for surveillance perspective point of view. In fact, this is a kind of a payload which is being integrated on top of the dome. Other condition monitoring structures can be, condition monitoring behavior can be effectively monitored using this flex sensors which are available. So in order to cater such kind of performance evaluation, so ideally this is a kind of a system which is being deployed where we have a load cell in place, then there is a rod, and then there is a soft jellyfish with a water channel which is available. So when there is a kind of a load which is exerted on this jellyfish, so appropriately we can see a movement, and these movements are being catered on the load cell, and from the load cell we can do the measurement. So ideally the measurement of thrust is catered using this load cell. So this is a kind of an actual jellyfish where we have the head and the tentacle, and this is a kind of a biomimicked jellyfish kind of structure. Even though it is used on a macro level, so it can be reduced on a micro level appropriately by incorporating certain amount of flexible bimorph based actuators, so that these bimorph based actuators can be has its own appropriate frequency which can be effectively used for the motion. So this is a kind of a movement with reference to horizontal perspective point of view, and this is a kind of a movement which is observed with reference to vertical perspective point of view. So here if you see we have seen this vortex motion which is getting created. These vortex motions are generated by the tentacles which are available. So this is a kind of a horizontal motion, and this is a kind of a vertical motion where we have a scale kind of structure. So these vertical motions are appropriately opened and closed, and then you can almost mimic the behavior. So when there is an expansion of tentacle happens, what happens is it will try to push the vortex force in this particular direction, which caters the overall movement in this particular domain. So almost in an actual condition also, the jellyfish follows the same phase, where the vortex motion is created in this particular domain, and then it will be helpful for the appropriate propulsion of the system. So these are some of the different positions of these jellyfish kind of structure with reference to time domain, how the results are deployed, and in order to cater the different loading conditions. So these are some of the testings which are being deployed, where in such a way that these SMA structures are integrated with these polyimide behaviors, and the payloads are deployed, and the actuation is happening appropriately. So this is the kind of a jellyfish prototype which is slightly on a macro level. So appropriately it can be on a micro level for the different applications or the characteristics. Okay. Now we will discuss about the micromechanical flying insect in the upcoming class.